Hello and welcome to a buildingSMART members webinar titled Multi-Scale Virtual Twins, Bridging the Gap Between BIM and GIS. Thank you for joining. My name is Ra Twilly and I will be your moderator today. The speakers for this session are Pedro Diez Cocero, AEC Solution Experience Manager at Dassault Systèmes, Andrew Bourget, CEO and CTO, as well as co-founder of ECUS, and Alessandro Pedretti, Business Development Manager at Edacom. The webinar is scheduled to last between 45 minutes and an hour, with a short Q&A at the end. The webinar is being recorded and will be made available for replay on our website. I'd like to remind you that your phone lines will remain muted for the duration of this webinar. If you have questions or wish to make comments, please use the chat function located within the control panel. I would also like to bring to your attention that buildingSMART is committed to ensuring that participation in the development of standards is unrestricted, and the process for their adoption is transparent, and standards that are developed do not favor any particular provider and are open, non-binding, and accessible to all. Please take note of our antitrust code of conduct. And now I would like to hand over to Pedro.
Thank you, Ra. Thanks for hosting us today. And let me take over this screen. Here we go. So indeed, what we're going to be covering today is the topic of multi-scale virtual twins and how we can use them to bridge the gap between BIM and GIS. And together with Alessandro and Andrew, we will be covering how we are addressing this specific issue with 3D experience. So first, let me start by drawing this picture of what a multi-scale virtual twin is and how we can bridge that gap by leveraging this type of virtual twin. So the idea is that in any asset, we have different layers of the information that is behind, starting perhaps from a virtual component that could be, for instance, a pump that needs to perform certain functions, that need to fulfill certain requirements, and that has some specifications associated, certain manuals, certain maybe even maintenance information. So this is typically captured at the virtual component level. But of course, this pump belongs to a bigger system. It could be the piping system of a building, where you have the smart asset layer, where this pump doesn't exist standalone. It exists as part of this system, and then it needs to guarantee certain throughput. It needs to perform under certain conditions with certain power, and it belongs part of this bigger system. So it belongs to this bigger picture. In the same way, we can continue scaling up, and we can see how this piping system of the building belongs to the smart building, a building that needs to perform certain functionalities, and that is, of course, part of a bigger built environment, which would be the city layer. And here, for instance, we would need to look at how this smart building is connected to the bigger piping network of the city, how it connects with the sewage system, for instance, of the city that is covered by the utilities network. And then, of course, the city is part of a bigger territory, which is, it could be a region, it could be a country where it needs to be subject to specific regulations, and where that scale is more like the authorities that are responsible for managing the sustainable growth of this kind of ecosystems. So as we can see, there's all these different layers that are interconnected and that represent the different scales at which we can look at a specific asset. And typically, when we look at IFC and specifically building design, we stay at the layer of building, asset, and component. But of course, it's very relevant to look at them from a bigger scale to address these kind of interactions that I was describing, where these layers are more typically addressed from a GIS standpoint. And traditionally, there exists this gap between the two that we are able to address with 3D experience. So let's have a look at how we're doing that. Before we get there, I think it's relevant also to explain how IFC is a very important enabler of this right-hand side of the multi-scale virtual twin, how it has been progressively growing to address different scales of the asset as well. and how with our 3D Experience platform, we've been committed since the very beginning to adopt IFC as a main enabler, as a main standard for supporting this building information layer for, of course, all the previous versions of IFC, including IFC 4.3, which is now released, and with the current implementation of IFC 4.4, that I think Andrew will be mentioning something about as well. If we look at how we address IFC with our 3D Experience platform, we crunch all the data that comes in an IFC file, we ingest it in our platform, and we convert it into our data model, where we have different entities that represent the behavior of all the different layers that are inside the IFC file, inside the building. And we're able to capture all the semantics and all the metadata that comes with the IFC file and assign it to these specific components. So that in the end, we have a data-driven referential that have parameters that can be searched, filtered, modified, and that represent accurately this component scale of the virtual twin. In the end, what we provide is a full data model that addresses all the different semantics that are part of the IFC standard, and that allow us to have this accurate representation of the virtual twin of the building, and where again we are committed to continue supporting the different versions of the IFC standard in the future. In the end, what you get when you import these IFC files into the experience is a connected virtual twin with, of course, the structure, the geometry, and all the attributes. But more importantly, that can be further enriched, that can be connected to other layers of information. It can be tasks, issues, documents that can be addressing the specific element of the asset that they are representing and that they are describing. And that can also be modified and further enriched, where we, of course, capture all the semantics or the metadata that is behind the asset in a faithful way that can be navigated and accessed by all users from the web browser. And this semantic allows us to interrogate the asset, to run queries, to filter, and to retrieve all the information that is relevant to make decisions across the different stages of the asset lifecycle. Now we've covered this layer of the at the building level, the equipment, component, system, and the building itself. But then we need to address, okay, this building exists in a greater built environment. So how we address the gap between the two. And what we have in the same 3D Experience platform, where we are able to bring in these IFC models, is a GIS engine that allows us to process GIS information and combine it with BIM in the same common data environment. So we provide this multi-scale referential from territory to equipment, and that allows us to bridge this gap that traditionally exists between systems that address these BIM and GIS separately. And where, well, in projects where exploring the asset in context can make a huge difference. And I have some examples, but of course, Andrew and Alessandro will be telling us more about that. So if we have a quick look at what's this multi-scale virtual twin and what we can do with them through the experience, it is that we have this very accurate representation of the built environment that surrounds our asset. It can be at district level, at city level, at territory level, where we can bring in directly the BIM model of our assets. Of course, we have different layers of geographical information in addition to the 3D. It can be anything from map views to orthophotos, CityGML. We also support multiple standards in that domain, with textured models as well, orthophotos, you name it. And the idea is that we can leverage this GIS referential at any stage of the asset lifecycle, since early on to run this concept analysis where we can already plan a basic shape of the asset in the context where it will be existing. And we can already leverage this referential to make annotations, understand what is it that the asset needs to fulfill in relation to its context. Once we have a more detailed representation of the asset, maybe coming from the IFC models that have been provided by our suppliers, we can directly bring that BIM model that has been imported from IFC and bring it into the GIS representation and into the GIS referential. And because it's part of the same common data environment, it can also be connected with tasks, it can be connected with issues, it can be connected with documents, and we can at any given time navigate the detailed representation of the asset, having a seamless connection between the GIS layer of the building, and the BIM detailed model of the asset, having again like this multi-scale virtual twin of our asset. Why is this so relevant? It's because we can have this bi-directional connection. So on one side, we can have the case where we have a GIS referential, maybe at city scale or territory scale, different layers that represent a specific district where we want to do the development of a new building or a new project. And we can make decisions based on the information that we keep at GIS layer. So for instance, information on the traffic and the surrounding areas, information on the certain public services that are available per district. And we can use this GIS referential to plan the development of our project. And at this stage, we're already able to bring in BIM detailed models directly into the GIS context. That saves lots of time in converting, simplifying, addressing the model. We are able to directly bring in this BIM model, see how it looks in the GIS referential, make annotations, and use that to keep feedback to the responsibles of designing the asset itself. And of course, the biggest value is that in this same referential, we keep these two views of the asset. So this is one way, bringing BIM into GIS, but the other thing that we can address is the opposite journey. So going from GIS to BIM, where what we're able to do is to extract specific area of the GIS referential where we want to do the design of a new asset. And then we're able to bring it into our own design context. This is in CATIA, embedded into the experience. And we can extract all the information of the terrain of the area where we are going to do the design. And we can use it as context for designing our assets. In this case, it's the interexchange of a highway. And what we can leverage is all the information that is in the GIS that is captured into the design context. So we can use that to do the design of our interexchange, making sure that it's respecting all the areas, all the parcels, or the properties, that is consistent and accurate in respecting natural areas, distances, regulations, all that. And once we have this representation of our asset, we can, of course, bring the detailed model, in this case of this exchange, and bring it back to our GIS referential, keeping an accurate representation of with the latest version of the GIS referential for asset itself. Something important to stress here is that it's not just a beautiful representation of the virtual twin of our asset. It has all the layers of a common data environment behind. So we're talking about being able to do issue management, leveraging this multi-scale virtual twin. We're able to connect documents that are related to the asset at any given level. We can do project management in the same virtual environment, in the same common data environment. We're able to manage requirements with full traceability on all the information, being able to have access to this golden thread of information connecting all the different layers of the asset. Where does this become relevant? Here I've highlighted a few examples. So anything from terrain work preparation, where typically you need to make sure that the asset that you're designing needs to be consistent with the terrain information, and we're able to do modeling in the same GIS referential of underground information with the geological properties and any kind of information that you would expect to do the terrain analysis. We're able to combine these two models to provide input for the contractor responsible for the excavation works, for instance. Another interesting use case that we are seeing more and more is for utilities network alignment. Typically, utilities companies, and especially in the transmission system operators, like the ones that we are starting to see in this new engagement of buildingSMART, they need to combine GIS information for the power lines that are distributed across large pieces of territory with the BIM detailed models of the substations that they need to model. And they need to combine these two layers. So by having both layers in the same referential, we're able to seamlessly connect the GIS information of the power lines that arrive to the substations with the detailed model of the substations themselves. Of course, once you have this GIS referential, it can be leveraged for monitoring projects. So if you have, if you're a subcontractor, general contractor that needs to keep track of many developments, many projects over territory, it could be over a country, for instance, you can leverage the GIS referential to master all the subcontractors that are responsible for the different parts of a project. You can check what's the status of the different projects. You can leverage all the metadata behind to track this information. Of course, this can become very relevant when integrating building design in urban context. So many cities, especially the largest ones, have strict regulations on the impact that new buildings and new designs can have on the surrounding context. So in order to guarantee this coherence between the new buildings and the existing ones, we can leverage this GIS referential, bring in the detailed model of the BIM of the project that we are developing, and making sure that it's consistent, there's not going to have a huge impact, that we can respect things like the amount of sun that the different buildings around it receive, that any kind of restriction that we need to fulfill can be tracked from this referential. For sure, for property development, this is very important, where companies, real estate developers need to maximize the value of their properties, and they need to be able to track the property value and study different concept designs. We can leverage parametric design to study different concepts and then make sure that those are consistent with the built environment that they need to fulfill. And finally, for construction site works, where when you're going to do already the construction process of a building, and you need to plan things like in which location you'll place a crane, which surrounding streets you need to cut in order to perform the construction works, what impact will that have on the traffic on the surrounding areas. We can study things like noise and the impact on the neighboring areas. So we can look at these different contexts and see leveraging this multi-scale referential of the asset. Of course, these are just a few examples, but I think it's more powerful if you hear this from Alessandro and Andrew, who are here with us today to show us how they are addressing this gap between BIM and GIS with 3D experience. So I would like to hand it over to Alessandro. If you're ready, can you take over the screen?
Yes, Pedro. Thank you very much. Thank you for your great introduction. Do you see my screen?
Yes.
Okay, great. Hello, everyone. Just a few words about myself. I'm Alessandro Pedretti. I'm a business development and BIM manager here in Idecom. So I try to support our customers implementing 3D experience platform as an enterprise solution for the project. This is the agenda I will follow during this webinar, my session. I will make a brief introduction on who we are at Idecom and what we do. Then I will fastly move to the project scenario. I want to talk about an old water system infrastructure built in the beginning of 19th, more or less, with the aim of giving you an overview of the methodology and the processes we adopted during this project into the experience platform. I will be more technical with respect to the background that Pedro give us a few moments. Our company profile. We start working as a civil engineer design company in
We are just losing your audio, Alessandro. Perhaps if you could turn your video off and see if that just comes through clearer with just the audio.
Okay, thank you. As I said a moment ago, we are oriented to innovation. So we have been always user of the system solution, and in this case, of course, 3D experience platform on cloud. And in the timeline, you see a significant event in our history, which has influenced the growth and the board decision of Idecom over the years. It was the creation of an internal R&D department in 2018, specialized and dedicated to the study of composite materials, specifically fiber reinforced concrete, and their engineering applications, especially in the infrastructure sector industry. And during this period, we have been able to use the structural and process simulation application implemented in 3D experience platform to digitalize and replicate the physical behavior of this type of material, trying to optimize it for the production processes that we also developed and patented to kind of 3D printing technique that we have also simulated as a production process into the experience with vertical application dedicated to robotics. Our specialized application of the experience platform attract the interest of the system AC industry. So in 2020, we start a strategic partnership thanks to our expertise. Now our objective is to be best consultant for our customer to introduce digital processes in their BIM project. Okay, let's jump to the project I want to talk about. During the last 6 months of the past year, we start building up huge, let me say, linear infrastructure of an aqueduct in Italy. 240 kilometers more or less of linear infrastructure. Start building, as I said before, in the beginning of the 19th and ended up in 1950, more or less. The infrastructure crosses almost 57 square kilometers of terrain, and it's largely made up of historical bridges and underground structure, tunnels, galleries that are still working. The owner, that is a public authorities, is in dates back more or less to the early 2000s with the construction of a new section of gallery. And the scope of the owner is to construct, to model and has built BIM of the entire system, modeling also the damages along the infrastructure, because there are a lot of failures due to landslide since the tunnel crosses a lot of different type of unstable terrain. So they need to build up not only a 3D BIM model of the entire infrastructure, but build a real digital twin of the existing one. And our challenges was to digitalize a lot of information, as you read in the video. We analyze a huge amount of historical data, starting from manual drawing to more recent 2D DVG and reports that helped us create the BIM model. In order to handle such huge models like this, you need to take in consideration the scale of the building and, of course, of the infrastructure like this that are comparable to the scale of a region, a large territory. So you have to talk about GIS. The ability to handle such a large assembly that is composed by more than 250 models, more or less, in a unique environment, a common data environment. So we use only one software, one solution to manage BIM data and GIS, geological information. And last but not least, you have seen the ability to perform simulation on the same data, and we make FEM analysis about the landslide, and we can see in the slide later. Okay. We built a real digital twin of the existing infrastructure that is, let me say, a full-scale BIM model with a level of detail high enough to represent also the damages along the tunnels. So as I said before, the extension of the project is so huge that we have to think about territorial scale. So we start building up the terrain and the infrastructure using open GIS database to retrieve all the territorial information as a source of 2D data that has been elaborated with the use of visual scripting, that special modeling technique into the experience platform, in order to create a parametrical 3D model geolocated in the right position in a GIS context. And so this will allow the end user to manage the resources on a territorial scale and ensure control over the asset, and of course make correct decisions based on the location of the asset and the conditions. The entire infrastructure crosses different types of unstable terrain, as I said before, and thanks to a series of geological information deriving from geological campaign over the year, it has also been possible to create the 3D geological model conditions that the aqueduct crosses, which help us to understand the exact position of the main faults that affect the infrastructure and that are the main cause of damages to it, causing also potential infiltration of dangerous chemical substances in the water. So thanks to the BIM model of the infrastructure and the model geology in the same environment, we are able to simulate potential landslide phenomenon that can impact the infrastructure. And 3D experience give us also the ability to control, in conclusion, the integration of all these data in a unique environment. That is a crucial step so using 3D experience as public authority can harmonize the asset, providing a large scale view as an entry the asset extended context to the all detailed information behind, as we said with Pedro a few moments ago. So making decisions at the scale of a singular equipment based on the interaction with the extended built environment. As Pedro said before, in 3D experience platform, all the AEC data model is implemented, of course, with the ability to import and export IFC file format. And 3D experience is also open to commercial data format coming from Autodesk, for example. For this project, we use 3D models coming from Revit and of course 2D drawings made by AutoCAD. So, but obviously, it is 3D experience is a platform open also to other CAD standards such as DXF, STEP, and so on. There are basically two ways to approach to data management in 3D experience. A file-based approach, let me say, and a PLM approach. In the first case, you import a 3D model, and in case of revision to the model, you need to import a new version again. In the second approach, with the PLM1, let me say, you connect to the experience with your BIM authoring tool. And in this case, you save the model from the original BIM software using a sort of plugin. No need to import export files. And in this way, you can manage the entire life cycle of the model, of course. This is a more practical video focusing mainly on the technique adopted to model some part of the infrastructure, since we need to fastly model in 3D many kilometers of existing bridges, respecting, of course, all the reports, the inspection reports coming from the maintenance activities on the field performed by the owner. So we need an efficient modeling strategy that would allow us to model quickly and meet the required timelines and milestones. What you are seeing now is a parametric template of a bridge that can reproduce a lot of different geometrical and typological configuration that cover all of types of bridges along the 240 kilometers of the track. So we collect all this configuration in one unique template, of course, connecting its IFC attributes and information. So physically, the user select a geolocation from, of course, also GIS data and other source. And then the template will automatically adapt, creating a new bridge model according to the rules you set it. So this will grow in the details thanks to the change of load functionality present in 3D Experience. That it means that using this poor geometry as input, let me say, as input, a new 3D model can be instantiated with more geometrical details. For example, the models of rebars, steel detailing, and so on, coming, of course, from a catalog of detailed parametric templates that are already built in 3D Experience. Of course, they can be exported according to IFC schema. This is another video I'd like to illustrate to show you the benefits of implementing GIS within 3D Experience platform. In particular, we focus on the power of the integration between GIS, BIM, and CAD, and how this integration can be a revolution for asset management. The first point to consider is the ability to integrate existing GIS information with BIM and CAD models of the asset in one unique environment without the need to import or export the files. And accurate view of our infrastructure in the context, having both 3D model of the building, the geological model, and GIS information in one place. And that can help a lot planning and management activities from the municipality, for example. In 3D Experience, you can leverage, of course, on GIS querying functionalities based on geographical information. So we can do geospatial analysis and quickly retrieve all necessary data to make the right decision, optimizing the necessary operations, let me say. Another key point is the increase in information traceability. With GIS and BIM integrated into 3D Experience, we can easily trace the origin and the history of each asset, improving our ability to monitor and manage the entire life cycle of the infrastructure. And as you can see now, using 3D Experience platform for our project, we can leverage on a structured data. It means that, as you have seen, the model has a hierarchical data. Let me put to the end. Okay. So in the model, you can also attach your data, for example, PDF for technical specification, or drawing also to the model, and you can easily query and find it via web using a web application. Okay. It's in the same work session, let me say, without need, of course, to import, export also in this case, we simulated a hypothetical landslide scenario, trying to assess the impact of such an event on a section of the pipeline. This is just a small example focused on the mechanical behavior of the structure. But 3D Experience platform is also used by other public administration, such as, I remember, Hong Kong and Singapore municipality, to support their decision adding air and noise pollution and all scenarios that can be simulated within the platform to test the benefits of mitigation actions and predict also possible critical impacts on people. There is a lot of more to talk about. I think I need two more hours. So I suggest you to follow our main channel and our LinkedIn page to discover more about the project. And that's all about me. Thank you for your attention. I leave the stage to Andrew.
Thank you, Pedro. Okay, so share my screen. Alors, just a brief word that Ecus, we're a contractor. We have our own design office, and we are involved in underground structures. So I just want to go through now what brought us to Katia, but with a specific focus on multi-scale virtual twins, which is really a key in our activity. So I'll just go through some of the technical issues that all civil engineers are well aware. Is the second you start going for a single source of truth approach, that is, you don't have multiple different files, everything concentrated, you're confronted with different scales. Here I got an image of the Geneva Basin with you can second guess the geology that's underneath the orthophoto. We've got the different geological faults that are present. So you need to get a grips of your general environment, as was said earlier. But then you've got to actually model your structure, what you're being paid for. And you must also place it into context with the neighboring buildings, not just in our case, the geology. And then you've got the other issue is that civil engineering is not the end all be all. It's just the container itself for a lot of mechanical equipment, electrical equipment. And these three contexts work with different tolerances. So if the second you want to start doing takeoffs, you want to start doing setting out drawings, you really got your work cut out to try and manage those different levels of tolerances. So we all operate in a legal context. The cadastre is always with respect to a local projection system. And you need to place your project in that legal context. We're not just sort of drawing it out of context. We really need to tie it in with what the building permit will require. So you need it not just on the surface level, but you also need it in elevation. Really, that is very important. And so you're confronted really from the start of a project with the problem of setting out your project. Then you need to, once you've determined, okay, you're operating in a certain part of France or Switzerland or wherever, you've got your own legal reference system, then you've got to manage your precision level. We operate with large range and normal range, which for civil engineering is, we found amply sufficient, which basically means large range is our geological models, our terrain models. So we're going from 1 millimeter up to 100 kilometers. And that's our in-situation models. And then when we go down to actually our structures, well, it depends. If we're talking about a tunnel that's 13 kilometers long, we stay in large range. If we're going into certain specific structures like shafts, then we will go back to normal range. And of course, all that is equipment, electromechanical equipment, electrical installations are all done in normal range, which is the millimeter precision, which is sorry, the micron precision, which is way beyond what we would expect as a civil engineer. So it's very important to have a system that can manage at least these two levels. Okay, CATIA offers 4 ranges, but we only operate in the two middle ones. Once I just give an example of a project we had here in Switzerland, which is the Transrhône. You've got up here, you've got La Chaux-de-Fonds, which is at 900 meters. It's the highest city in elevation in Europe. And you've got Neuchâtel down here. So actually, the difference of level is 900 meters. And you're confronted with local structures. You don't just have a single tunnel and that's it. You've got stations, you've got various ancillary works. And so you need to zoom in, you need to break down your project into components. And so you must be able to superpose plot delimitations, you've various information, GIS information, and your structure. And okay, it's maybe a bit small, but you've got here the tunnel meters, or the project meters to be more precise. And if, of course, you change your alignment, these will change, and it will have an effect on all your local structures. So you can't just say, oh, I will study one shaft totally independent of my alignment. You can't, because you're going to get all sorts of issues, starting with where it is along the alignment, because if the alignment numbers change, then you need to get that up to date. But of course, elevations, your shaft is not so high as in a previous iteration. So really, you've got this constraint of tying in your local structures, which may be quite small, to a larger project. Of course, Pedro showed a bit of the geology. The geologists work in a totally different scale from us. So we need to integrate that. So here we've got the geological model that's 15 kilometers by 15 kilometers, in which it has helped us do the alignment, make sure that we're not intersecting any critical geological incidents that would render the project too costly or too technically challenging. So this is very important. And there we work in large range. And then you've got this interaction that you need to get hold of. We've just seen the very large, the large range, the normal range is your structure, but it has to tie in with the local environment. It has to tie in with the buildings. And how we go about it is we immediately at the start of a project, we define a reference, a georeference point. We place it on the terrain model that we obtained. We define its, of course, its projection references are predefined, and then we just determine where it is. What's the altitude? What's the northing and easting coordinates? And we will then tie in all the project based on that reference. It's got a system, CATIA, of publication, which facilitates the cross-referencing between different components of the project. So you axe your work based on how you're going to set it out. Then you've got the issues, sort of mid-size issues. We go in large range here, which is calculate the basin, what's the flooding risks, what's the how to dimension the drainage. So the drainage is quite small, pipes of 200 or 300 millimeters. And on the other hand, you're talking about a surface area that's kilometers squared. So you really need to have these two levels within the same model. And then you will overlap that with GIS information that's publicly available. And then lastly, I just want to go through the fact that you need to understand that at one point, well, we probably all understand it, but at one point we're working with third parties, subcontractors or suppliers, and they will be working in their own reference system. So we must have that in mind when we go to work, and it's one of the specifications we define with our suppliers. For example, here I got the lift system with all the details. Each structural member is defined. We've got our stair manufacturer that supplies us with that information. We've got electrical components that we need to integrate into our structure. So we need to change the level of LOD. CATIA calls change LOD. So you start up with a level 200, you go to 300, you go to 400. When you're going over to 400, you'll start integrating your suppliers' models. And that's very important to have this various level of tolerances in your unique model. There, thank you. I'm open to questions. It was a fast run through of the various issues that you need to manage if you want to have a single source of truth. Thank you.
Excellent. Thank you very much, Andrew. Really good to see all that, and bring us straight to the Q&A part of this presentation, and reminding attendees, if you have any questions, please use the chat function in the control panel, and we can get to those. So starting with a question from Catherine, which was at the end of Pedro's presentation. The question is, would you say that the connector between the different layers is the geospatial coordinates? If so, is a minimum accuracy level defined for all or by layer?
Yes, I would say that Andrew has already answered that question through his presentation already, but the answer is yes, the coordinates can be the connector between all the different layers, and no, there's no specific accuracy that you need to define for all layers, so you can work with different accuracies for the different layers that you're working on.
Okay, thank you. Another question. Is it possible to combine two projection systems, e.g. for projects and borders between two countries with two different CRS? So Andrew, could you address that, please?
Yes, well, as Pedro was saying, what we do is we define two sites, each one with its own reference projection. We had the case for the CERN, where all or most of the geological data was actually in France. And so we superposed the French system and the Swiss system, one on top of the other. So you can actually mix systems. I also do it just to complete that it's cross-border, but we also have a lot of issues with boreholes, old boreholes that used to be in the old Swiss reference system. And so we have to integrate old boreholes into the new geological models. And again, you can play with that. You can have each subcomponent of your project tree can actually have its own reference system.
Thank you. It looked like there's a lot of complexities and challenges you're having to deal with in your projects. Would you say it's getting easier with how the software is developing, or is kind of the complexity getting greater in what people are demanding, how you're keeping up with all that?
I would compare it to what's happening with the software, what happened to the software industry. When I was a young engineer, I learned Fortran 77. You could virtually learn it in an afternoon, and you would take 5 months to make a small program. Nowadays, you need a PhD in computer science, but it takes you 5 minutes to make the same program. I think we're basically on that path where the step level is getting higher and higher, but projects are getting thus that you can produce much more in a much shorter period of time. But the initial step, the entry criteria are much steeper than 10 years ago.
Yep. And where would you see this going within the next 5 years, say, for what do you think is going to be possible, and some things maybe that are challenges now that hopefully will be resolved by then?
I think one of the things that I feel that is underestimated is our education system. I'm 60, and I produce the drawings because as I'm doing the thinking through, and I produce the drawings. I used to have draftsmen. I'd have 2 or 3 draftsmen doing the various things, and they would actually check that the curve in the alignment of the road was as per the standards. But now all that is built into the software, so you're basically you don't need draftsmen anymore. You need engineers that are good technicians, and it's a paradigm shift that universities just totally oblivious of. And I think the main challenge for us is to get the education system to align with the industry.
We say that to add to that from the perspective of the software providers, I think there's 2 layers, right? One is how much this software is changing and will for sure change drastically over the next few years. There's already a few revolutions in our industry in terms of how we are addressing automation, parametric design, with some of the examples that Alessandro was showing, for instance, and we are growing massively in that direction. So one is like the one variable is how much the software will evolve, and for sure artificial intelligence will play an important role in years to come. And then the second aspect, the second variable, is how quick that can be adopted by the industry, and how much of that can be implemented in projects, and how fast construction projects, the entire construction ecosystem can adopt this new technology and implement it in real life cases. And I think that there will be like these 2 paces that will move progressively and need to work hand in hand. So for sure, what Andrew is saying about like having a solid education system that allows to transfer the knowledge from the software providers that are creating technology to the end users will be a very important aspect.
Thank you. That's really helpful to hear, and it's going to be very interesting to see how that all evolves over time. That's brilliant. And for people who are sort of new to potentially using this software and getting into contact with you, what's the best way for them to learn a bit more and get in contact?
From our side, you can definitely feel free to reach out to me directly. If you want to learn more about Dassault Systems, there's a lot of information on our website, on LinkedIn, on YouTube. And actually, for Alessandro, if you want to comment on how to get in contact with you and learn more about Idecom.
Yes, of course. Yes, of course. You can reach me on LinkedIn. That's my only social web. Also for Idecom too, we manage a company official page on LinkedIn on our website.
And for Andrew, I don't know if you want to answer like how to reach out to you.
Yes, well, you go to our website, contact@ecus.ch, and we're always out to look for talent. So if you've got questions on Katja, it's great, and if you've got questions on the company, it's even better.
Perfect. Thank you all. Well, we've reached time, so I'd like to take this opportunity to thank all our presenters, Pedro, Alessandro, and Andrew, and also thank our attendees for their participation. So thank you, everyone, and look forward to where all your work is headed. It's all brilliant stuff you're doing. So good to see, and thank you for your time today.
Thank you.
Thank you for having us, Ra.
Thank you very much.
Smart.
Thank you. Goodbye.